The main mission of the Institute for Flow Physics and Control is to study fluid flows and then to apply that knowledge to flow control applications.
The Institute is unique in the sense that I don't know of any university facility in the nation that has the wide variety of experimental facilities that we have here.
The Institute has 22 faculty. In terms of students, it supports 75 PhD students, which I believe is the largest fluid dynamics program in the U.S.
We have a large number of faculty working in areas that are similar enough to make us a cohesive group, but also different enough that we each have our own unique research pursuits and interests.
Industry provides us with the types of problems that are technically relevant, and then it helps us to then focus on the type of flow physics that we can use in order to solve those problems. Plasma dynamics, acoustics, complex flow fields. This is just a small essence of what we do.
My work with plasma examines the interaction of plasmas and electromagnetic waves. Plasma is a very interesting dynamic electromagnetic medium. We can control the electromagnetic properties of plasma, and so we can control how waves propagate through them. My work is related to optics in the sense that we're trying to create plasma adaptive optic devices. We can form a bulk region of plasma, and in this region we can control the index of refraction. This idea could be extrapolated to allow us to do things like full spatial wavefront control or high-speed beam steering. This work could be used to develop high-speed plasma adaptive optics for wavefront control that could revolutionize the field of aero optics. Additionally, plasma adaptive filters could push the boundaries of existing stealth technology.
Much of the work I do is involved with flow through gas turbine engines, and air-breathing engines are the technology that propels almost all commercial aircraft. And so they're extremely important to the aerospace industry and to the American economy. The work that we do involves studying how flow moves through the engines at very unique conditions. They're very high pressures, very high temperatures, very high speed flows. That provides a very unique set of conditions that enable the engines to perform the way they do, and at the same time that provides unique opportunities for us to study airflows in these really unique environments. The facilities we've developed are important because they simulate the same temperatures, pressures, and flow speeds that you would see in a gas turbine engine. So by simulating these, we can do fundamental research in a small-scale laboratory, but at the same time, we can have research that is directly applicable to applications and manufacturing. The work we do is involved with both inventing and understanding and maturing new technologies that will help the aerospace industry.
My particular research area is computational fluid mechanics. My focus is on multi-phase flows. We do what is called direct numerical simulations of multi-phase flows, where we follow the evolution of complex flows in great details on very large computers, often on the world's or the nation's largest supercomputers. We use the result then to come up with what is called reduced order models to enable us to make predictions in practical situations.
One of the things that's important in developing improved aerodynamics and system performance is to thoroughly understand the relevant flow field, the fluid mechanics. And the first step in that process is to look at the global effect of the flow, and that's best done with flow visualization. So that typically involves the injection into the flow of some type of seed particles and then illuminating those seed particles, and we can get sort of a global feel for how the flow is behaving prior to going in then and doing more detailed point measurements.
Fluid mechanics probably affects every aspect of your life. So understanding fluid flow and how to apply it in the optimum way really impacts almost your entire well-being. This is a very exciting time in many ways for the Institute.
The Institute has a great future. I certainly anticipate will continue growth with more lab space, more opportunities for students to learn and have more impact on society.
Our future lies in what we do best, and that's coming up with inventive solutions to highly complicated aerospace problems.
We're always pushing forward, we're always adding new facilities. I like to say there's room at the top, but not enough to sit down.